So for the next part of Chapter 9, we're going to look at the reactivity of alkynes, which is pretty similar to the reactivity of alkenes that we learned about in Chapter 8, right? Those 10 or so reactions we've done. And so here in the notes of the next couple of pages, I've included sort of a brief refresher on alkene reactions, and we'll find that reactions with alkynes, these triple bonds, are going to be pretty similar, right? And a lot of things we can do to alkynes, we can also do to alkenes and vice versa. So this is kind of pulled straight from the book, and I will say, just to not have any confusion here, a couple of these reactions, I believe it's just these two, we didn't learn, but they're in the book, so you can ignore these in particular. All right, so let's start looking at some alkyne reactions here. And so one thing we can do with alkynes is actually turn them into nucleophiles. So if we remember from our Chapter 8 or Chapter 2 notes, right, learning about acids and bases, we know that alkynes, right, these sp carbons, have a pKa of about 25. Okay, and that's in comparison to, right, alkanes, right, just simple sp3 carbons, which have a pKa much higher of about 50, and alkenes have a pKa somewhere in the order of I believe it's like 35 or so, right? So these alkynes, right, while not as acidic as even, say, water with a pKa of 16, are still pretty acidic. So what we can do with these is we can react them pretty readily with a strong base. So we note up here, right, that this basic form of ammonia here is pretty basic. And so what we see down below will be the mechanism for this. So if we do this reaction with this conjugate base of ammonia, right, really strong base, go ahead and draw in our lone pairs here, we can see that it can pretty easily abscond with the hydrogen, right, leaving lone pairs onto the alkyne to make our acetylide, which is what this group here is, acetylide, this negatively charged alkyne, right? The conjugate base of an alkyne is this acetylide, okay? And so now with this alkyne handy, we can go ahead and do further reactions with it, because now it itself is nucleophilic, right? It's also a stronger base, but now, right, as we can see here, it is nucleophilic. And so what we can do, for example, with this next reaction right here, hopefully it looks a little familiar, we can do an SN2 reaction with it, right? We have our polar protic solvent, right, DMSO, and then we have our primary halide here, right, with this bromine on that primary carbon, right, which is great for this nucleophilic attack. And so for the mechanism for that, right, we have our lone pair on our conjugate base, right, this nucleophile, come in, right, do this backside attack and have bromine leave as the leaving group. Like this, right? And we know all our carbons are here, right? 1, 2, 3, 4, 1, 2, 3, 4, and then our alkyne here is still there, and R, hopefully you've learned this already, but R is sort of, it means any number of carbons, essentially. It's kind of just a catch-all for when we don't want to write out all, any number of carbons there. So this is sort of the general way to, quote-unquote, synthesize an alkyne from an acetylide, right? We're taking an alkyne and attaching it to something else, right, to make this longer-chained alkyne, right? So we've gone from a sort of external alkyne, where the alkyne's at the end of a carbon chain, and now we have an internal alkyne, right, where the alkyne is in the middle of a carbon chain. All right, so for this next reaction, we're going to look at something a little bit different, but it has the same sort of general format here. So we can actually react these acetylides with carbonyls, because carbonyls themselves are pretty reactive. So if we remember from Chapter 1 in our general chemistry knowledge, there's a pretty significant dipole here between the oxygen and the carbon. And so if we illustrate that here, right, the oxygen is partially negative and the carbon down below is partially positive. Right, so these carbonyls, right, this carbon double bond into oxygen, are pretty electrophilic, right? That carbon is kind of void of electrons, right? It wants more electrons. So it'll be the source of this addition of nucleophiles. And so we'll see that illustrated here in just a second. But we can have this nucleophile here come in, right, attack that carbon, right, that electrophilic carbon, and push those electrons from the double bond up onto that oxygen to get us the following. So now we have the oxygen here that's negatively charged. That methyl group hasn't gone anywhere, and now we have this alkyne attached to our reaction here. And so the next step, right, is this acid here, right, this H3O+, and we can illustrate that in a mechanism like so. This is essentially just quenching the reaction, right, making everything neutral at the end, because negatively charged oxygen would much rather be neutral. So we use an acid to sort of help fix that. And so our final product here from this initial ketone, right, this carbonyl, is the following. Right, so now we have this alkyne as our final product here. Okay. And you notice there's no stereochemical control here, right? Because notice we have a chiral carbon, but we just get a mixture of enantiomers, right? Because this sp2 carbon, there's no way to control whether any of these groups will be on wedges or dashes. It's all sort of random, again, because of the planar nature of this sp2 carbon, okay? So in short, right, when we're adding these acetylides to carbonyls, right, we're going from a ketone to an alcohol. So for this last way to make alkynes, right, we've seen alkynes attached to things, but now we're going to go ahead and look at a way to make an actual alkyne, right, starting from an alkane. And one way we can do that is similar to what we learned in Chapter 7, is by doing an elimination reaction. And we can see here, right, on our reaction arrow, that we have all the conditions set up to do an E2 reaction. Right, we have a strong base, polar protic solvent, and heat. What you want to notice is that we have two equivalents of a strong base, right? So we're going to do that E2 reaction not once, but twice, okay, to make our final product here. So let's take a look at the mechanism of this to see what this looks like. So one thing I am going to change here to kind of illustrate a point is I'm going to put these on wedges. Right, because remember we want these E2 reactions to be right, anti-periplanar. We want that hydrogen to be 180 degrees behind the bromine when we're doing these elimination reactions. Okay, so this first equivalent of KOH is going to react with our reaction here. Right, and this hydrogen, right, is 180 degrees behind that bromine, right, they're on opposite sides. And so this intermediate here will be the following, right, with our alkene getting generated, right, this molecule flattens out. There's no longer wedges or dashes, we just have this planar molecule. And so for the next step of the reaction, we're going to say step 1, step 2, we're going to use a second equivalent of that KOH. To attack the hydrogen here, right? It's going to eliminate now this bromine, right? And it's still 180 degrees behind the bromine to get us our final alkyne here, right? So hopefully that makes sense. So this is another way that we can do the sort of alkyne generation, right? Starting from this dihalide, we can react this all the way to an alkyne.